Hello everyone. In this session, we are going to discuss about the neuron concept. What is the neuron and what are the supporting concepts? So, in this, we are going to deal with the neuron, expressing the linear perceptrons as the neurons and feed forward neural networks, and also some uh, activation functions like the sigmoid, tanh, linear, and like that. So, the neuron. Neuron is the fundamental unit of the human brain, and it is having the biological neuron, it is having the number of inputs. There are three steps. The neuron will take the input from other neuron and it will process the information and it will send the information to other neurons. So here you can see that here this is a neuron. In this neuron, the dendrites, these are having the inputs. They will take the inputs and in the cell body they will strengthen and sum and transformed, and then it will be produced as the output using the axon. So that this is the basic structure of the human brain neuron. So we have to, in our computer science, we want to design a unit looking like this. What's like this? So how can we design that? The neuron, we can translate this functional environment into the computer science related neuron. So let us have the input. The input is in the form of the vector, that is x equal to x1, x2, x3 and so on, xn, meaning that n number of inputs are there. This is the input vector. And we can develop the neuron like this. See here, all these vector input, they are given as the inputs to the neuron. This is the neuron, the bubble is the neuron. And for each input, we will have the weight, corresponding weight. These weights, actually in the previous topic, we discussed about these weights only with the symbol theta. So here the theta can be represented with the W1, W2, W3 and so on, Wn. So here n number of inputs are there. So n number of W's are also there. So they are giving as the input to the function, that is the neuron, that will be represented as the function, and inside the function, the initially wherever the input was given along with the weights, the weight vector is the weight vector that can be represented with the W, Wn, W2 and so on, Wn. Once it received the inputs and the weights, then it will calculate the sum of the products, that is called the linear sum. We can call it as the linear summation of the product of weight and the input. So see here, z equal to, we are representing that summation with z. So z equal to sigma I equal to 0 to n. We can represent this with 1 because we are starting with the w1. So we can start with the 1. So I equal to 1 to n. So and wixi. Wixa, W1 into x1, W2 into x2, W3 into x3. We have to sum of all these and we will make it as the z. And then that z can be given into another function, so that will produce the output. See here, y equal to f of z. So this will be given as the input to this function. That function will perform some activation. So there are various activation functions that we are going to discuss in the coming slides. Okay, so that can be represented like this, y equal to f of, here the same thing we are representing in this way, f of x into w, x dot w, that is also called the x into w plus b. Here what is b here? The b is another input, that will be the bias. We can call it as a bias or intercept. In our machine learning, in general, we are calling this as the intercept, and here we are calling it as the bias. So, in the previous session, we have seen that the machine learning hypothesis, the hypothesis will be h of x comma theta equal to -1 or 1 based on the value given by the equation based on the given theta values. So we have taken that theta 1, theta 2 as the 3 and 4 and theta 0 as minus 24. This is the bias here. If it is less than 0 then minus 1. If it is greater than or equal to 0 then 1. The same thing can be represented with the neuron, that can be represented like this. See here, x1 is the sleep, x2 is the study. We are taking this from the previous session only. Example, based on the sleep and number of hours sleep and number of hours study, and how it is related with the performance of the student. So see here 3 and 4, here this is the input, this is the input 2, and these are the weight 1, weight 2, and this is the bias, the y will be given, so that we can represent that f of z in this inside the neuron, f of z equal to minus 1 or 1. Here we may get either minus 1 or 1. So if z is less than 0 then it will be 1. If z is greater than 0, greater than or equal to 0, then it will be 1. So see here, the z is here 3x1 plus 4x2 minus 24. That is the equation of z, and minus 1. How it is transforming that value into between minus 1 and 1, that is called the activation here. So inside that there will be the activation. The z will be given as the input to the function, and it will convert that z into minus 1 or 1. So this is the linear perceptron. This is the linear perceptron, and how it is working. And our brain is having number of neurons. We talked about a single neuron. Our brain is having the number of neurons and with the different levels of layers. So how it will be performed is like this. See here, you can observe that here these are the inputs. We are having 3 inputs, and we are having number of another layer of neurons, and this neuron is connected with all the inputs. This neuron is also connected with all the inputs. This neuron is also connected with all the inputs. And then the next level, we are having one more layer. Here this neuron is connected with all the neurons of the previous layer, and this neuron is connected with all the neurons of the previous layer, and so on. So here in this, we have to understand one more important point, that is, we can zoom it. Yeah, we can zoom it here. So if you see this here, how this W1, 1 and 1 as the superscript. See here, the W1 means weight. As we discussed, for every input there will be the weight. As we discussed, every input. Here I1, for I1 there is a weight. That weight is, what is that weight means? Here, this is the weight 1, this is the weight 1 for input 1, the weight 1 for input 1, that is for the neuron 1. This is the neuron 1, we can call this as the 1 neuron, and for the first neuron, weight 1 for the first neuron, and this is the weight 2 for the I2, for I2 W2 is there. This is also for the 1 neuron, first neuron, and this is the W3. W3 is the third input weight, and this is the this is for the first neuron. And if you come here, this is the second neuron. This is the weight 1, that is for the I1. This weight is for the I1, so W1, and this is for the second neuron. This neuron is second neuron, and this is the weight 2, and for the neuron 2. This is the weight 3 for I3 for neuron 2. And here is similarly, here also W13, weight 1 for the neuron 3, weight 2 for the neuron 3, weight 3 for neuron 3. This will be represented as the subscripts. In the subscripts, we will represent the weight number and the neuron number. And a superscript, you can observe that one more superscript is there. That superscript will represent the layer number. This is the first layer, so that we are having this. If you go forward on the top, we are having this here. In this W1, 1, meaning that weight 1 for the first neuron and weight 2 for the first neuron, weight 3 for the first neuron, and here weight 1 for the first neuron, weight 2 for the first neuron, weight 3 for the second neuron, weight 3 for the second neuron, and so on. Here if you observe that it is similar to previous one, but the layer number is 2 because it is the second level of layer. So in this way we can represent the weight numbers also. So these layers, actually this is the input layer and this is the output layer. These layers are called the hidden layers. We can call them as the hidden layers. So we can go with this. The connections only traverse from the lower level to the higher level only. You can observe that in the previous diagram, from the lower level to higher level, you can see the arrow marks. From lower to higher level, there is no backward direction. So see here, and then there are no connections between the neurons in the same layer. In the same layer, there is no connection between the side, meaning that for the same level of the neurons. And there is no connections that transmit the data from the higher level to lower level. There is no such relation. And because of this reason, these networks are called the feed-forward neural network. Feed-forward network. Now you can see that there is no connection between these two neurons. There is no connection between these. There is no connection between these two neurons. And there is only one direction from bottom to top, and there is no relation between the from top to bottom. There is no connections. Okay, so this is about the feed forward neural network because we are going forward only. There is no back propagation. Okay, so these are called the neural network with the feed forward neural network. And now there are some key points we have to understand. The layers of the neurons between the first layer and the last layer. Between that, they will be sandwiched layers. We can call them as the sandwich layers. They are called the hidden layers. So the layers between the input and the output layers, they are called the hidden layers. And one more thing, in general, how many number of inputs are there? Let us say, for example, if you have the 10 inputs, the next layer, the layers should be compressed by layer, so the compressed representation will be there for the network. So actually this is not compulsory, but it is the better way of representation. And it is not required that every neuron of the current layer should be connected to the every neuron of the other layer. There is no rule for that. For which neurons of the previous layer should be connected to the neurons of the next layer, that is the deciding that is an art. Okay, and with the experience we will get that. And the inputs and outputs are the vectorized things. So meaning that the inputs are vectors and outputs are also vectors, and they are in the linear perceptrons. These are called the linear perceptrons, and the